When you look at a complex electronic circuit, it can just be a tangled mess of components, right? A total web. But what if there was a way to figure out what a circuit does without getting totally lost in how it does it? Well, today we're going to dig into a really powerful technique for taming that exact complexity. Let's jump in. Okay, imagine this. Someone hands you a sealed box. Inside, there is a circuit, but you have no idea what it is. All you've got are two pairs of wires sticking out, an input and an output. It could be an amplifier, it could be a filter, who knows? So how on earth do you figure out what this mystery box actually does? That's the big question we're tackling. So on the left, you've got the messy reality of what could be inside that box, a total spaghetti monster of components. But here's the thing. For our purposes, we don't actually need to trace every single one of those connections. Instead, we can use the super elegant solution you see on the right, the two-port network model. We just treat the entire circuit as a black box and focus only on what we can measure at the input and output. It is a brilliant, brilliant simplification. Now, before we can start poking and prodding our box to figure it out, we've got to establish some ground rules. See, this model has its own language, its own set of conditions that have to be met for our analysis to be right. So let's take a look at the fundamental language this box speaks. So here's the formal definition. Really, a two-port circuit is just any network where we've decided we only care about the relationship between what goes in and what comes out. The guts of the circuit, we completely ignore them. All that matters is the behavior at these two ports, which are just pairs of terminals. Now, to describe everything this box does, we only need these four variables: the voltage and current at the input and the voltage and current at the output. Pretty simple, right? But here's the absolute crucial insight. They are not all independent. The physics inside that box creates a fixed relationship, which means if you define any two of these, you can always calculate the other two. For this whole black box idea to actually work, the box has to play by some rules. First, no stored energy. You can't have, say, a charged up capacitor in there when we start. Second, no independent power sources, no little batteries hiding inside. Third, whatever current goes into one terminal has to come out of the other one in that pair. And finally, no cheating. We can only make connections at the designated ports. All right, we've got our box and we know the rules of the game. So how do we actually figure out what's going on in there? This is where the detective work begins. We're going to start probing the circuit to uncover its secrets, and these secrets are what we call its parameters. These parameters, they are the secret code we are looking for. They're the numbers, the coefficients that link our four variables together in a nice, clean set of equations. For example, one parameter tells you exactly how much the input voltage changes when you change the input current. If you can find these parameters, you've basically written the instruction manual for the black box. You've cracked the code. So how do we find them? It's actually way easier than it sounds. Let's try to find one of the so-called impedance parameters, Z11. Simple. First, you just leave the output port totally disconnected. That's an open circuit, so no current can flow out. Then you apply a voltage you know to the input, and you measure the current that flows in. The last step? Just divide that voltage by that current. That's it. That ratio is our parameter, Z11. We can find all the others using similar little tests. So we've done our tests, we've found the parameters, we've cracked the code. Now what? Well, now we get to use this for some really practical analysis. You can think of it like having the official technical specification sheet for our black box. I absolutely love this analogy because it's so true. The parameters really are the circuit's DNA. And just like real DNA, this code is what makes modular design possible. It tells any engineer everything they need to know to predict how this thing will perform. It means you could swap this block out for another one with the same DNA, and the whole larger system would still work perfectly. It's the key to interchangeability. And this is really where the rubber meets the road. With these parameters in hand, we can calculate all the key things an engineer actually cares about. We can find its input impedance, basically how much it loads down whatever is feeding it a signal. We can calculate its voltage gain and its current gain, how much it boosts or cuts the signal. We can even find its Thevenin equivalent, which is just a fancy way of saying we can create a simple, standard model of how its output will behave. This is the heart of practical circuit design. But the real magic, the ultimate power of using this method comes when we start connecting these well-defined little blocks together to build much, much bigger and more complex systems. So what happens when our one little black box is just a single piece of a much larger puzzle? How do we analyze the whole shebang?
So here's our starting point. One single block. It's fully characterized. We know its parameters, we know its DNA. Now, what if we have a second one? Each is a known quantity, a predictable little building block, all ready to go. The real power here isn't just in analyzing one box, but in understanding how they combine to create something much more complex. So let's do just that. We can connect them in what's called cascade. All that means is the output of the first one feeds directly into the input of the second one. It's just a chain. And this simple chain is the fundamental structure for everything from multi-stage amplifiers to massive communication networks. And this right here, this is the ultimate payoff. Instead of trying to analyze one giant, impossibly messy circuit, we break it down. We analyze smaller, manageable blocks one at a time. And for a cascade connection like this, there's a specific set of parameters we can use that lets us just multiply their effects together to get the result for the entire chain. This modular approach isn't just a trick. It's the foundation of modern systems engineering. So you see, the two-port model isn't just a tool for calculation. It's a mindset. It's about taming complexity by deliberately ignoring the messy internal details to focus only on what matters, the inputs and the outputs. It transforms a problem that looks hopelessly tangled into a simple series of predictable building blocks, which kind of leaves us with one final thought. Now that you know the strategy to simplify and connect any complex system, what will you build?